I is change in head over length, and the length gets dropped out through the, oh man, I'd have to go back to the derivation. I can't do it just off the top of my head.
That's okay.
I can go back and do the derivation if you want. Want me to?
You're fine. It's just helpful, like, to see connections from the
Let's
basic
do it.
equation.
It's not hard. There. I don't want to give you bad information. And this is something that I have to think about myself from time to time, so. Class stuff. Lectures. It comes down to this little slide right here. Okay, so we're looking at one particular flow channel in our flow table. And we have equipotential lines here that are dashed. And so we have approximately square elements. L3, L3, L2, L2. They're not perfect, but that's the assumption that we make. Okay? So we know that flow equals Q equals K times, right now this is just I, so that actually should be velocity of the channels. K times I, so that's change in head divided by the length. That's this guy right here. Okay, Ki. But that's also going to equal, if that velocity, because the velocity and the flow are going to remain constant through that channel, we have change in head divided by this length here. That's going to be the same as this one. It's going to be the same as the next one, and so forth. In other words, the flow has got to remain constant through that whole channel. Think of it like a pipe. And so the flow through that pipe is going to be the same. So what we find is that the change, what do we know about the change in head between here and here versus from here to here? They're the same. The change in head is the same, as long as the equipotential drops are equally spaced. So that's going to be that change in head. Well, actually, that's the change in head of the whole system, from the first to the last, divided by the number of drops in between. The number of headlines in between. It's interesting. You can do the math. If you see it, it works out. It's fascinating. And then all we need to do, that would give me the flow. And by the way, when I say flow, we're looking at one. The reason why it is flow, actually, because area is equal to a unit area, one unit area into the board. This is a two-dimensional drawing. But if I want area, it's got to be the cross-sectional area through the flow channel. And so, but say I've got multiple flow channels. So if I want the total flow through all those flow channels, all I have to do is multiply the flow through one channel times the number of channels that I have. And that's where that NF comes in, the number of flow channels. So this times the number of flow channels gives me my flow for one unit area. If I know the area of that third dimension, the length basically, then I can get the actual estimate of flow. But I mean, that's where that comes from. That's the derivation. That's my I, basically, K times I. So let's go back. Where were we? We were right here. So, well, K would be given. What's my change in head on this one?
6.
It's going to be my total change in head, right?
Yeah, 6.
So 6. K times 6 feet. How many flow channels do I have?
3.
Yep. 1, 2, 3. 3 flow channels. And how many equipotential drops?
1.
Starting here, because that's where the drop of water starts. It's going to travel 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 to get to the end. 12 drops. And then you can do the math, and that would give you the flow for 1 unit length into the bore. If we knew the width of this dam, then we could compute an actual flow in terms of volume per second. Okay. So those are all the things that we could get from a flow dam. And you will be tested on a flow dam. So it's good to know these things. Okay? All right, I want to talk about phase diagrams for our good friend Jeffrey, and I think it'd be good for all of you to review. The hard thing with flow net problems is you can't really make them up because all the numbers have to work. But why don't we just at least talk about the steps of what we could do? Okay? And let's just review some concepts first of all. If I take a glass of soil, soil could have solid particles in it, and in between the solid particles exist what?
Voids.
Voids. But what exists in the voids?
Air.
Air or water. So if I just then take the sum of all the mass that's inside my little glass and divide that mass up according to its what it is. So I'm going to break up and I'm going to lump all the soil, all the solids, right down here in the bottom of my glass. And then I'm going to lump all of the water that's in the voids in this portion, and then the leftover air in this portion. So the total volume would be the same as the soil that was in my glass before. All I've done is just broken it up into its different components. Okay? So we could describe this in terms of either volumes total volume, the volume of the voids. So this is basically the volume of everything that's not solids or soil. Volume of air, volume of water, and then of course the volume of the solids. Or conversely, we could describe it as what? In terms of what? Weight. What do we say about the weight of the air?
0.
We just say it's 0, that's right.